Hello, everyone. Thank you for joining us today. I'm Christine Liu, Product Manager of Advantech Edge Intelligence Solutions. Today, I'm glad to invite our partner, DeepSeek, deep learning software engineer from Intel, to speak with you about how Edge AI is changing the field of medical images with higher accuracy and improved workflow. DeepSeek, would you like to greet the audience?
Hi everyone, my name is Deepthi and I'm from Intel. I'm excited to be here today and join Christine in talking about the increasing importance of Edge AI in the field of medical imaging.
AI and deep learning achieve higher level of accuracy in image diagnosis and also help to streamline the workflow. According to recent study from Defective Healthcare, one-third of hospitals and imaging centers have reporting using AI, machine learning, or deep learning to add in tasks associated with patient care images or business operations. With AI algorithms detecting abnormalities quicker than the human eyes can, AI has ability to drive more efficient task flows. This was proven in our recent collaboration with Intel and Heroic Face Medical Science. As a consequence of the global COVID-19 pandemic and the need for remote monitoring, Heroic Face has developed an AI-powered long-sum continuous monitoring systems. Powered by an Intel 9th generation Core i7 CPU with Vega AI acceleration modules, driven by 8 Intel Movidas Mira X VPU for AI analysis. Inferencing is also optimized using the Intel OpenVINO toolkit, reaching an inference efficiency of 4.51 frames per second. In this project, Heroic Face used the Intel OpenVINO toolkit for running multiple inference operations in parallel with performance optimizations. DeepSeek, can you elaborate more on how the Intel OpenVINO toolkit helped optimize deep learning performance for healthcare images?
Yes, of course. As we know, AI techniques and in specific neural networks are increasingly becoming adopted in the field of medical imaging. These techniques, such as object detection and segmentation, help the radiologist quickly identify issues, resulting in many benefits, including better patient outcomes and reduced cost for the hospitals. To facilitate optimized inference for these neural network models, Intel has open sourced a toolkit called OpenVINO. OpenVINO enables easy deployment and acceleration of neural network models on Intel platforms. It has a write once, deploy anywhere kind of architecture, supported through an inference engine runtime that provides hardware specific acceleration. There are two main components of OpenVINO: the intermediate representation of the model that can be read, loaded, and inferred with the inference engine. The second part is the inference engine, which is a set of C++ libraries that provide a common APIs to provide inference results on the platform of choice, such as CPUs, GPUs, VPUs, or FPGAs. The inference engine is based on a plugin architecture, which means the plugin for each device contains the complete implementation of the kernels required to do the inference on the specific hardware. The inference engine enables device-specific inference, but also provides hetero and multi-modes for inference performance on multiple devices. There are additional performance optimizations that can be used, such as asynchronous mode, which allows for pipeline execution of the inference requests, and multi-stream mode, which allows for running multiple inference streams in parallel, resulting in better core utilization. Now I would like to briefly talk about the steps involved in utilizing OpenVINO inference optimizations. The first step is to build the model, also known as the training step. This is done on the model architecture, and that is done using a training dataset. Once the trained model is available, Optimized inference can be obtained by converting the model to an intermediate representation using the model optimizer and then load it into the inference engine and run on the target hardware, which can be any Intel Xeon processor, Intel Core processor, Intel Atom processor, Intel processor graphics, and Intel FPGA, or an Intel Myriad Vision Processing Units, also known as APUs. In addition, OpenVINO provides other component parts to satisfy the developer's every needs. OpenVINO contains an open model zoo that provides an optimized deep learning model for download through a model downloader script. OpenVINO also contains a post-training optimization tool which provides support for quantization to enable low precision inference. The post-training optimization tool is easily configurable and can be run through a command line interface. It also provides Python APIs to build a custom optimizations pipeline. OpenVINO also provides a scalable, high-performance solution for serving machine learning models called the model server. The model server is implemented as a Python service and is optimized for Intel architectures. The model server can be enabled on bare metal hosts or in Docker containers. In addition, OpenVINO provides the dev cloud for quick prototyping for developers. These optimizations have allowed us, in many cases, to demonstrate a significant performance improvement in deep learning model deployment, and in medical imaging use cases as well, demonstrate several fold improvements in performance.
Can you also give us more examples?
There are a few use cases that I would like to talk about today. The first two are the bone age prediction modeling use case and the lung segmentation model use case from Philips. These sophisticated deep learning models from Philips are used for segmentation and classification of images to help the radiologist identify issues faster. The bone age prediction model is based on exception architecture and takes X-ray images of human bones to determine the predicted age from the bones. This helps identify underlying medical conditions if the predicted age for a younger patient is less than the actual age. Using the OpenVINO toolkit, Philips was able to achieve a speed improvement of 188x over the baseline for this use case. This was achieved through a number of OpenVINO optimizations such as node merging, batch normalization elimination, constant folding, and also running multiple instances to achieve higher throughput. The second use case from Philips is a lung segmentation model based on unit architecture that identifies lungs from the CT scan of a patient's chest and then creates a segmentation mask around the detected organ. This can be used to measure size and volume of the lungs or for disease screening such as for tuberculosis or pneumothorax detection. Using the interdistribution of OpenVINO along with additional optimizations such as Vinograd and resampling optimizations, to this model, a performance improvement of 37.7x was demonstrated compared to the baseline inference performance. GE Healthcare, a leading provider of medical imaging equipment, was able to leverage OpenVINO to classify and tag scanned image slices to make them easier to find. The team was able to achieve a 10x improvement over the baseline, far exceeding their throughput goal using no burnt and 4 dedicated cores of an Intel Xeon processor.
Thanks for sharing, Deepsi. Advantech has been working closely with Intel to develop edge AI solutions that support the Intel OpenVINO toolkit and enable AI medical imaging applications without driving up the cost. In fact, the AI inference phase can drive as much as 90% of the application computing cost. Therefore, it's really important to choose an edge AI platform that can deploy in deep learning at scale, while balancing AI performance with a reasonable total cost of ownership. Advantech Vega 300 series AI acceleration modules provide a perfect solution with excellent performance, scalability, low power consumption, and are reasonable price. The Vega 300 modules are powered by Intel Movida's Mira X VPU and offer M.2 mini PCIe and PCIe by 4 interface options, which allow easy integration with medical systems using Advantech USM ARC AIMB Conf series products. With Vega AI modules integrated and the Intel OpenVINO toolkit, a CPU-based medical imaging system can perform optimized inferencing without increasing the cost and without requiring modification to hardware deploying in the field. Take the heroic phase case for example. The Vega 340 AI module can support 4-channel long-sum analysis running at 1.12 frames per second, resulting in 4.51 images per second, which is quite good performance. Moreover, Advantech provides Edge AI Suite software which integrates to OpenVINO toolkit to enable accelerate deep learning inferencing on edge devices and to monitor real-time status via a GUI dashboard. It supports a diverse range of deep learning frameworks, such as Conf, TensorFlow, and Onyx, and it provides pre-trained models such as YOLO V3 object detection and human pose estimation. Customers can leverage Edge AI Suite to accelerate their AI inference deployment. Advantech also provides AI training servers such as Air 300, which is based on Intel Xeon processors and supports NVIDIA high-performance graphic cards to deal with complex, high-resolution and real-time image analytics in medical solutions. Customers also can choose an Advantech Sky Series 2 4U server which supports up to 6 Vega 340 AI modules for heavy workload requirements. In response to the COVID-19 pandemic, Advantech also provides the AI-based face view industrial app, which can perform real-time ID recognition, facial face detection, and body temperature management with high precision. FastView works perfectly with Advantech Air AI systems for infection prevention at all access points in hospitals. We provide an SDK for further development and real-time visual dashboard tracking. FastView also optimizes performance up to 5.4 times under OpenVINO on the VPU and reduce CPU loading by 72%. Advantech provides both hardware and software Edge AI offerings to help you easily deploy AI in the healthcare field. Finally, we come to the end of this session. Thanks for your attention. It's an honor to be here with you today. Hopefully, this presentation has been beneficial and helpful to your solution.